In example 7.8, we're going to return to the loop-the-loop roller coaster. And this time we're going to ask several questions. First question is, what's the minimum speed required at the top of this loop to ensure that the car makes it around the loop and doesn't fall down? And then, given that minimum speed, what would be the speed at the bottom of the loop? And finally, how many G's does the rider experience at the top and at the bottom? So first, let's just think about what's going on when a roller coaster makes a loop. So when this car is going around the circle, there needs to be a centripetal force changing its direction, because otherwise, if the car were here and there were no centripetal force, it would just continue in a straight line. So the centripetal force is whatever forces are pointing toward the center of the circle. And it turns out that the two forces that are doing that are the normal force between the track and the roller coaster car and the centripetal component of the gravity force. At the top and the bottom, those are the easiest places to analyze because gravity points exactly along the radial direction. At other points along the track, gravity makes some angle and the geometry gets trickier. But everywhere along the track, the normal force between the track and the car points toward the center of the circle. That's because normal, perpendicular, everywhere on the track, because it's a circle, the perpendicular to that circle points toward the center of the circle. So for a circular track, the normal force always points toward the center. It's a centripetal force. So let's start out in part A by drawing a Freebody diagram for the top of the track. And then thinking about what is required for the minimum speed for the car to make it around. All right, at the very top, the downward direction points toward the center of the circle. So my R direction, my radial direction, is straight down. Here's the roller coaster rider. I'll just draw their face, their upside down face. And at the top, there's the gravity force. And there is the normal force. Remember, normal force is always pointing normal to the track or perpendicular to the track. So at the very top, normal force would be pointing straight down. And there's no forces in any other direction. That's it. So the sum of the forces in the radial direction equals mass times centripetal acceleration. And both of these forces are pointing inward, so they both get minus signs. That centripetal acceleration is also inward, it gets a minus sign. So all these minus signs cancel out. All right, now here's the key thing. When you have the minimum, no, let me back up. Imagine that you're not going fast enough to make it around the circle. imagine you're going too slow so that by the time you get to the top, you start falling. If you're falling, that means that there's no normal force. The roller coaster is no longer in contact with the track, so n equals 0 if you're not going fast enough and you start falling. If you're going really, really super fast, the whole time you're sort of smashed against that track and there's a large normal force pushing against you. So at the very threshold, that transition point between being able to make it around versus falling, that's the instant when normal force equals 0. So our criterion for the minimum speed is that n equals 0. If you were designing a roller coaster, you would want to make sure that n is a little bit bigger. It's not exactly 0, so you can have some wiggle room to make sure that people don't fall off the roller coaster. But this is the absolute minimum required. So that means mg equals mv squared over r. Those m's cancel, and we get v equals rg square root. So that's the minimum speed required at the top to make it around. And that criterion, again, was that the normal force goes to 0. All right, so assuming that we're traveling at that minimum speed, and then gravity just takes over, how fast are we traveling at the bottom of the loop? This is just a conservation of energy problem. Potential energy plus kinetic energy at the top is potential plus kinetic at the bottom. We're ignoring friction and air resistance, so there's no external work. At the top of the loop, that potential energy is mg times the height. Because this has a radius of r, that means that the height at the top of the loop is 2r, the diameter. And the kinetic energy at the top is 1/2 mv squared, but we already found the v at the top. V squared is rg. We just undo the square root. Potential energy at the bottom is 0. It's at ground level. And the kinetic energy at the bottom, well, we're kind of solving for this. We'll figure out what that is in just a second. All these m's cancel. We can multiply everything by 2, so we have 4gr plus gr equals v at the bottom squared. Yep. So we get v at the bottom equals 5gr square root. 4gr plus another gr is 5gr. Okay. That was just a conservation of energy problem. We didn't use any circular motion stuff. Now part C, how many G's does the roller coaster rider experience at the top and at the bottom? So let me remind you of the definition of G's. Unfortunately, this is another one of those cases where we're using the same symbol to mean different things. we already have this g, but that just means 9.8 meters per second squared. This g is something different. It means what is, I'll write it down mathematically. It means what's the normal force that the person's experiencing in terms of, or relative to the person's weight. So how many times greater is the force they're experiencing than the force you're used to in everyday life just from your weight. So at the top, the rider is experiencing 0 G's because our criterion at the top was that n goes to 0. And if you ride a roller coaster, the feeling of 0 G's is that feeling of weightlessness. Like, this is pretty thrilling if you're going on a ride. Feels maybe a little scary. 0 G's at the top. You feel weightless at the top. At the bottom, well, we need to do another quick Newton's second law analysis to figure out what the normal force is at the bottom, because we didn't figure that out yet. So let's draw a quick free body diagram. There's the rider at the bottom of the loop. Keep in mind that at the bottom, the radial direction toward the center of the circle points up. So there's the center of the circular path. Gravity, of course, points down. But now, normal force, because the track is underneath you, points up. The normal force always points toward the center of the circle, and at the bottom, the normal force is pointing up, whereas at the top, the normal force was pointing down. Okay, so we've got that circular version of Newton's second law. Now we have to be careful with the signs. The radial direction is up, so we've got minus n and minus w equals minus mv at the bottom squared over r. So n equals, let's get all these signs right, w plus mv squared over r, or mg plus m 5gr, oops, square root, over r. A little more algebra. We've got mg plus 5 mg. Those r's cancel out, so that's 6 mg for the normal force. And according to our definition of g's, normal force divided by mg is 6. So at the bottom, you're experiencing a force on your body 6 times what you are normally experiencing. You feel very crushed. So if you've ever ridden a ride like this, you know that the sensation you're feeling is at the top, you're weightless. It almost feels like you're about to fall. bottom, you're getting crushed. You're feeling smashed by the ride. And 6 Gs is not healthy for a human to experience for a long period of time. But the time period over which you're going to experience 6 Gs is a fraction of a second. So you're not going to be in danger. If this was sustained for